Hello, everyone, and thank you for joining today's free ZNCD webinar, Architecture at Zero, Design Solutions for School Decarbonization. As you get settled, please feel free to say hello and where you're joining from today in the chat. To qualify for continuing education credit, AI California provides the learning objectives for every webinar and includes them in the presentation that can be made available online. A few quick housekeeping reminders. Today's session is being recorded and qualifies for one AIA HSW learning unit and 1 hour of ZNCD MCE. For those who stay on and watch live, AIA California staff will report these units to AIA for you and will provide ZNCD certificates to those who qualify. Please use the Q&A function to ask any questions for today's presenters. You can also like a question to move it to the top of the queue. Please be constructive in your comments and questions to help foster a positive learning experience for everyone. I'm so pleased to introduce our speakers for today's session. First, we have Dave Intner, AIA, Architect and Certified Energy Manager at Southern California Edison; Charlie Boyd, Architect and Studio Manager at Design Draw Build; Sin Gao, Architect at Macmillan, Pasden Smith Architecture; Jin Huang, Project Architect at Goodwin Mills and Cowwood; Stephanie Perez Ocaranza and Belina Nguyen, both students at Cal Poly Pomona. Thank you all so much for being here, and I will now hand it over to Dave to kick us off. Thank you so much.
Thank you, Sarah, and thank you everyone for attending today's webinar. Looks like we got a really great, robust attendance and a lot of interest in seeing these creative and innovative solutions that these project teams will be presenting today. So I'm going to do a quick screen share. Okay. So just to kind of provide some context for today. So the Architecture at Zero program is led by AIA California and brought to you by Southern California Edison, PG&E, and SoCalGas, the investor-owned utilities in California who fund and support the initiative. The 2024 Architecture at Zero competition focused on decarbonization, resilience, and equity. The competition challenge was to design a new building on a middle school campus in East Los Angeles, the Griffith Steam Magnet Middle School, within the Los Angeles Unified School District. You can see here the overall project campus, and then in yellow, the actual project site where the design of the um, project occurred. So the new building was to replace relocatable classrooms, which include science labs, an art classroom, a maker space, outdoor learning environments, and a teacher workroom. Participants were also required to prepare extensive analysis detailing the projected energy performance of their solution. While the competition location centers on a real world site, note that this is an ideas competition and is not necessarily intended to result in a real, ultimately built project. Nonetheless, the thought provoking solutions proposed by the competition entrants and winners, sourced from an international pool of submitters, will no doubt inform future projects, especially considering the conversations occurring around decarbonization, resilience, and equity in the context of rebuilding from the recent Southern California wildfires. So I'd like to take a moment to note that all of this year's winners and the past competition winners are available on the competition website at www.architectureatzero.com and that planning is underway for the next iteration of the competition. Those interested in participating in the future should send an email to info@architectureatzero.com, and we'll put that in the chat so you can see it and have access to it. Send that email to be notified about future competition timelines if you'd like to participate. The projects being presented today are a mix of both outstanding professional work as well as an exemplary student entry. We'll be exploring the following projects: the Honor Award winner in the professional category, a Gualta steam engine by Design Draw Build Incorporated of Oakland, California, and presented by Charlie Boyd; the Merit Award winner in the professional category, Link Plus by Macmillan Pasden Smith Architecture of Columbia, South Carolina, and presented by Jin Gao and Jian Huang; and the Merit Award winner in the college student category, The Courtyards, presented by Stephanie Perez Ocaranza and Belina Nguyen of Cal Poly Pomona. And so with that, I'd like to turn it over to Charlie Boyd to present the Igualta steam engine.
Hello, everyone. How are y'all doing today? Probably all muted, huh? Um, so this is the Igualta steam engine. This was our design for the 2024 Architecture at Zero competition. And I wanted to walk you through kind of what influenced our design and how we used energy modeling to refine it. So I'll start with so sort of the scheme that we started with was just based on the program analysis. We kind of decided we wanted to have hubs of the classroom and lab spaces around like central open vertical circulation. Like these are all two-story buildings. And then there's like a large workshop space, maker space, and we wanted that to be centered between those. And then, so that's this guy here. And then as we think about sort of the circulation from the existing campus, you know, you have access here, you have access along here. If you're coming from the school, there's a couple ways to do that. And also the existing school has these lovely large courtyards. You know, they're these kind of narrow courtyard buildings with large kind of quads. So that sort of bulged into this central courtyard that kind of mimics that, but has this more organic form. And that sort of squishes things to one side and turns these sort of cells into kind of more croissant shaped things. And then thinking about the internal circulation here, like within these and how we spread things out a little bit. And then once we sort of rationalize that to a grid, what does that start to look like? Those spaces get a little bit more rigid and defined. You know, we wanted to use a modular grid. We wanted to think about, we were interested in designing for deconstruction and potentially like using reclaimed wood as like re-engineered structural materials for this like mass timber grid that we end up proposing. And then a big thing of it was like thinking about what is the school to a community. And in a lot of places, a school is like it's in addition to being a school, it is also like a meeting hub, a community space. You know, you have a flea market in the parking lot, or you have, you know, adult education classes on the weekend or something. And the fact that this had a makerspace too, and in East LA, there's like a big culture of working on your cars and stuff. And we wanted to, you know, we're a design build company. We wanted to encourage some sort of like vocational training that could maybe take place in this makerspace. So thinking about that being sort of potentially publicly accessible, it partially contributed to like why we curved that facade. And then just like thinking about the central courtyard. And then thinking about it as a kind of climate hub as well. You know, as there are increasingly common extreme weather events, a lot of communities, especially sort of ones that have been traditionally kind of disinvested in, don't have the resources that they need, especially in a crisis. So we wanted to think about this as, in addition to being sort of a social meeting point, of also potentially being a like distribution center in times of crisis, or you know, it's part of the program is that it's going to have these big batteries. The batteries don't need to just serve the school. They could be something where, you know, if your power's out, which maybe you have rolling blackouts in this area, you know, you can go here. There's these like these big water towers I'll talk more about, like if there's a drought, if there's a fire. I'm trying to think about how you create neighborhood scale climate resources, climate resilience. Yeah, so those were the ideas that we were kind of working with and how that started to influence the form. And then like, so this is what it looks like in site plan form. One thing that was part of the program was that there are these learning gardens to the north of the site, or it's sort of, yeah, it's north. That we're integrating sort of into the program here. This is like an outdoor classroom that relates to that. Here's that courtyard that I mentioned, and then sort of cutting away at the floor plates as they go up. So you have the courtyard, and then you have these like open spaces, and creating these like vertical, like double height open spaces and this sort of like porosity in the floor plan and in the floor plates to encourage cross ventilation, to allow natural daylighting down into the ground floor where we have these open vertical circulation collaboration spaces. So that's one thing we did, is that in the middle of the vertical circulation cores that we created between these little hubs of labs and classrooms, we also created these like collaboration spaces that can be they're open, they're not really programmed, they're these double height outdoor spaces that can be used for all sorts of things. The thing that I kept thinking about them being used for was, did you guys, if you ever did like an egg drop in science class where you have to like make a parachute for an egg and you drop it from the second floor and see if it survives? That was something that I could see happening here. I don't know if that's a middle school thing, but I enjoyed it when I was a kid. We have the maker spaces are centrally located, and you have this sort of axis that comes in. And then from the street, it's kind of rectilinear, it's kind of regular. And the thing that stands out is these water towers. You don't see a whole lot of water towers in new buildings these days, but they are kind of an icon of LA. And we wanted to think about, how do you make this iconographic? How do you make the sustainability goals of a project something that is reflected visually? And like, I think these are our attempt to like create something that like sparks some curiosity about like, well, wait, why did they do that? Like, what are those for? And I'll get more into that. But first, I'm going to show you this pretty picture again. So we cut away at these floor plates as they go up, so we can get more light into these spaces, and so you can have these nice shaded walkways and open walkways, and these double height spaces with trees popping through, and then big green roof, a lot of solar panels. Yeah. And then looking from below at the courtyard level, these are some people playing in the outdoor classroom. We didn't like fully do all the entourage. This is a competition project. We are a firm, so we had to limit the amount of time we could spend on it. So it went into the design, and I think the renders are nice enough that, you know, if we had more time, we would have done more with the renders. But yeah, so you can see all of these double height spaces that bring, or these double height open spaces, the openings in the floor plate that bring light down into the building. And then this like modular timber grid that we create with these cool posts that nestle into this sort of waffle slab grid. And yeah, so this is the idea in these little hubs, that even though we're on the ground floor, it's not a particularly tall floor, but you've got this double height space in the middle of it. This is that sort of community outdoor space that I was mentioning. And then because of these openings in the floor plates, you get all this abundant natural light in there. A big driver of the plan development was the analysis that we did of the daylighting and how we could minimize using the electric light by providing an adequate amount of daylight for the vast majority of the spaces for the majority of the time that they're being used. So that as we did analysis of that, you know, we started with like a conceptual sort of schematic massing model. And we looked at, well, okay, this probably shouldn't be a classroom because it only has daylighting 15% of the day. So maybe that's going to be the mechanical space, and we'll move this classroom over here. So like that was an interesting way that we worked, where I haven't previously done that, but I found that really helpful to be able to like look at individual spaces and be like, what is this appropriate for? And sometimes it's really obvious if you've worked on a lot of projects. And sometimes there's like surprising insights that you get from the analysis where you're like, oh, I would have thought, but I guess that overhang, the way that works, maybe the daylighting is not as good as I would have anticipated, or vice versa. So that was a big part of the energy analysis. And then, of course, we have a big water tower. And why did we do that? So that started from the program asked us to do big batteries. Like we have a battery electronics storage system. And those just look like big rack mounted servers, basically. But it also said that, we encourage you to look into alternative energy storage solutions. And we like that. So we started thinking about what that could look like, and thought of like, okay, how do you, if you're storing energy, you're talking about potential energy, right? So our first thought was to do a giant rock that moves up and down, kind of like the Michael Heiser sculpture at LACMA. There's a big rock that's suspended that you walk under, and you're like, ooh, I'm under a big rock. But that doesn't make sense. So we found something called pumped micro hydroelectric storage, which is basically you have a big engine. It's like a turbine in one direction and a pump in the other direction. So basically it can pump water up, and then when you want to reverse it, the water flowing down with gravity turns the turbine and generates electricity. So we decided, hey, why don't we do that? They don't really exist in a lot of buildings, but they are becoming more common. They work primarily in much larger buildings than this. The typical way to do it is if you have like a reservoir and a pump at the bottom of like a dam. So this is an odd scale for this, but things get miniaturized over time. Maybe this will be feasible at some point. And by involving water, there's all these multi-benefits, right? You can do rainwater catchment, and that can provide the water. The water coming from these tanks can be used for our chilled beam hydronic AC system, or like, environmental control system. What else? Oh, batteries don't work so good if you run them all the way down to 0, or if they get too hot. So like the optimal point for a battery, if you want to increase the lifespan of the battery, is between about 20% and 80%, 30 to 80 or something like that. So one thing that this can do is, even though this hydro system does not generate a ton of power, what it can do is it can prevent you from running the batteries down too low. And we can also use the water to circulate for like cooling the batteries. So keeping them at the optimal temperature and keeping them in like their preferred sort of range of charge allows those batteries to last much longer. Like we're talking decades longer than their sort of typical shelf life. So yeah, so once you start thinking about systems, you can start to think about how they can benefit each other. And these sort of multi-benefits start to stack on each other. And then also, obviously, water in a state that has been in drought for, decades, off and on. It's nice to have a little bit of extra water, especially if there's a wildfire and certain neighborhoods, their fire hydrants don't work because Pasadena, or all these mansions in wherever, are sucking up all the water to protect their giant mansions. So yeah, so again, community, climate resilience, resources was kind of what we were trying to do. And like we wanted to do some like reclaimed water treatment and storage as well for the rainwater and wastewater reuse. So we did some diagrams about that. And this is more or less what I just talked about, but in a cartoonier way. But yeah, mechanical systems, kind of talked about those. So yeah, radiant heating ceiling panels, the water goes into those. We're using ceiling fans so that we can minimize the amount of cooling that we need to do. And like, this is all stuff where if you have a robust energy model, you can plug all these different variables in and see how they affect each other. And like, I didn't know that adding ceiling fans, like if you have air that's moving, it feels cooler than air that's still. So that's one of the reasons cross ventilation is so nice, but that's also a reason that ceiling fans are nice. Because not only does it feel nicer, but it also reduces the amount of energy you have to use in cooling that space. So this is kind of conceptually, this looks kind of crazy, but basically the idea is, another thing about schools is they're not typically used on the weekends. So if you have solar and batteries, you're using electricity throughout the week, but you're not really on the weekend, but you are generating a lot of electricity on the weekend that you're typically not using. So if you have this hydroelectric storage that can also provide electricity, you can prevent the batteries from running down. But you can also, and that can also create like a buffer, so you don't need to draw, or so you don't, what was I trying to say? Yeah, so when you have solar electricity production that's in excess of the loads that are used in the building, that can recharge the batteries, basically. So we have this cycle where sort of the batteries are allowed to draw down over the course of the week, and then they get recharged over the weekend, and the water picks up the slack. From our initial baseline design, we like optimize the energy use like 70%. And a lot of that is based on speccing the right things, identifying these multi-benefits between them. And then like you just saw in that previous diagram, a big part of it is thinking about when systems get used and how you schedule things, how natural ventilation impacts what HVAC needs to look like, how circulating air can help keep the temperature more comfortable, how, you know, this water can be cycled within the building before coming in or before going out, and you know, can be this, you can create this sort of internal cyclical economy of resources. You know, and like simple things like having occupancy sensors during off hours, so you're not using lighting when you don't need to be. Additionally, with like daylighting sensors, yeah, all sorts of good stuff. And again, this is a competition project, so it doesn't have a real budget. So we can look at all of these interesting technologies and think about how cool they are and how they can work really well together. And then ideally take them home and use them in our real projects. And maybe not all of them, maybe I'm not building a water tower into a home I'm designing, but I'm probably going to think about the daylighting in a different way than I did prior to doing this competition. I'm going to think about how the systems relate to each other in a more sort of dynamic way. Yeah, so we also calculated our monthly end use energy consumption. The gray is sort of our baseline design, and the optimized is the lower one. And you can see even like here in the humps during the summer, when you would typically use a lot of power, we're actually using even less than we are in the winter time, because we're relying so much on cross ventilation and using passive shading and other passive design strategies and stuff. Excuse me. Yeah, there's a lot of detail in here. And then decarbonization strategies. I'm personally really interested in trying to maximize the use of like bio-based finished materials and reclaimed materials, and trying to divert waste, construction waste and stuff, trying to minimize the carbon in materials. We work with a structural engineer that has developed like straw insulation panels that kind of work like SIPS panels, but instead of having a bunch of foam inside, they have straw, and they're modular and they fit into a standard framing grid. So we said, hey, you guys have pretty good R values for those. Let's use those in our energy model and see what it looks like. And it's good. And you know, it's this renewable thing that you don't have to put a bunch of polyiso or whatever in your walls. You know, because a lot of these things, they're also good for human health. And we have, you know, if you're designing a school, you're designing for kids that are in a, you know, they're developing mentally and physically, and you really don't want to be putting more VOCs and toxins into their body than you need to be. So that's another thing of thinking about this campus as sort of an oasis within a neighborhood that like is pretty close to the freeway, has a high incidence of asthma as a result of just like the smog. So trying to make this a respite from that was big. And I'm not going to go through this, but I did a cool wall section. I had fun doing it. But we got rubble trench, we've got marmoleum floors, we've got daylight optimized LED lighting, we've got these modular radiant panels that we found. Thought about a way that we can use this like waffle structural grid, but just sort of like do it halvesies inside the rooms if we need to run ducts above it. Yeah, I think you guys are all gonna get this presentation if you would like to peruse it at your leisure. So I'm not gonna go into this too much, but also one thing that I didn't touch on is we try to have like natural pollinator planters outside most of the classroom windows. You'll see that in some of the renderings. We wanted, in addition to like making this a nice space, we wanted to generate a sort of nature connectedness feeling between the students and their environment. And like their immediate neighborhood does not look very nature. So trying to bring it into the school is really important. And that's the end of my slides. Thank you very much for your time.
Thanks for that awesome run through, Charlie. A lot of information, a lot of great data to present in a very short amount of time. This would be a good opportunity. I'll remind folks that the full entries for all of these projects are available on the Architecture at Zero website, and we'll put that into the chat so that you can bookmark that link and go into more detail in some of the entries as you would like to follow up. But of course, a recording of this will also be available as well. So with that, we'll go ahead and move on to our next presentation. So we'll go ahead and kick it off to the Link Plus project team of Jin Gao and John Huang.
Thank you, Dave. I'm going to share my screen. Can you see that?
Yes,
Yes, we can see it.
we're still seeing a couple of the black boxes on the screen. There's like a one in the bottom right that's a little big.
Okay. Oh, Sarah, can I have us to share the screen?
For me to share the presentation?
Let me try it again. Sorry about that.
I know earlier we had only a small one that wasn't in the way, so we're trying to get that back.
You're still here?
Yeah.
Yeah, the one in the lower right, if that might be a dialog box, you can close out from Zoom. Same thing with the upper right, yeah.
Okay, so I had the floating meeting control. Is that okay this time?
We got rid of two of
I
the
be-
three boxes.
Yeah.
There's
I
one more in the
believe-
lower right.
I believe the lower right block will not cover important information. You just go ahead. It's fine.
Okay.
Mhm.
It's still there.
Yeah, I have no problem sharing my screen. You just have to let me know and I can advance the slides.
Yeah, so Sarah, please help me share.
Yeah, absolutely. No problem. I know we love technology. Can you see my screen
This
okay?
works. So like before the meeting, I tested with Jen. It works good, but I'm not sure why this time it doesn't work.
No problem. Can everybody see my screen?
Yes, it looks great.
Okay, great. Just yeah, go for it. Thank
Okay, thank you, Sarah, and thank you, Dave. Hi, everyone. Thank you for joining today's webinar. My name is Jing Gao, and together with Jian Huang, we would like to share our project Link Trust. Next, please. Oh, this is the site. Dave already described the site condition, but we can see the existing image on the left. The first one is some temporary classroom on site, and the other two is the existing buildings and the entry courtyard. Next, please. When I first understood the set conditions, I wanted this project to feel connected both to the campus and the people. So it's not just a school building, but a space for learning, community, and daily life. And next, please. But the key focus of this competition is decarbonization. So I'm thinking, how can decarbonization become more than a technical checklist? Next, please. And I didn't want to treat a sustainable strategy just as something separate or added on. Instead, we made it as a driver of our design. So today, I'd like to share how decarbonization not only influenced, but actually shaped our design. Next, please. So the first, I will talk about how the decarbonization shapes our set plan. Next. This is the campus map highlighted with the black is our site. We create a central courtyard at the end of the existing campus path making a natural connection. And next. And we oriented the building east-west to reduce heat gain and improve daylight. And we divided the building into 2 blocks grouped by the thermal need and also to maximize the daylight. Like I said, we create a central courtyard. This courtyard are aligned with the prevailing wind direction from the east during the day and west at night. We also separated pedestrian from vehicles, using the building itself as a buffer. This promotes safety, workability, and also better for the environment. Next, please. Here are our early sketches. We use 2 curvilinear lines to save the building and the courtyard, and but we choose the second concept as our main direction. Next, please. And this is our final set plan. In addition to optimizing the layout and the circulation, we also focused on integrating low carbon landscape strategy and some solar responsive design. I will talk about it next slide. So you can see this area rendering capture our co-design response. The co-linear form of the building follows the natural flow of the site and gently guides circulation and creating a welcoming transition from the existing campus. So you can see the existing campus on the top right. And along with the curvilinear facade, we have some outdoor learning space, maker space, and a terrace. And you can also see a bridge on the second floor to connect these 2 blocks. Let's zoom into the courtyard. Next slide, please. And this is a rendering from the courtyard. You will see the permeable paving and a running path to reduce runoff. And we also use an amphitheater step to deal with the elevation difference and create a space for learning and gathering. And the native plants reduce water use and add some sensory richness. And next, please. Secondly, I'm going to talk about how decarbonization shapes envelope. Next, please. We use rimmed earth for the linear exterior wall. Rimmed earth is a local source of material with mineral processing, reducing emission from the manufacturing and transport. And the double layered rimmed earth with insulation keep the classroom cooler during the day and warmer at night. And it also served as a high sound insulation support focus and quiet. So the rendering on the right is from the second floor on the terrace. And so you can see the rimmed earth on the exterior wall. Next, please. And here is a rendering of the art classroom. And you can see the nature texture is a wall. You don't just see it, you can feel it, the room, the earth. And because it needs no finish, that means we save more materials and emissions. And for the next one, I'm going to talk about the curved courtyard facade. Actually, we integrated some building integrated PV panel system for the facade toward the courtyard. We begin with a direct sense study to determine the optimal placement for PV panel, make sure we maximize solar energy generation without compromising daylight access or views. And next one, you will see how the facade looks like. Next, please. And we designed this facade use 3 different types of glazing. The opaque panel for maximum energy generation at dense direct sunlight area. And the semi-transparent drawing actually is about 49 transmittance glazing to balance the shading and the light. And we use totally transparent area to preserve the view at the ground level. And this layered strategy allows the envelope to perform on multiple levels, generating energy, controlling heat gain, and enhancing indoor light quality. So you can see how it looks like on the top facade drawing. And you can also see how it looks like in the section. And next, please. In addition to the facade, we also installed 49% transmittance BIPV skylight and 34-degree tinted PV system at the roof. And all this together, this system generates about 400,000 kBTU electricity annually. It will offset about 69% of the building's total energy consumption from the grid. Next, please. And this side-by-side comparison illustrates the impact of integrating PV panel into the building design. So on the left, this is the annual hourly average emission and energy. The green line shows hourly energy demand, and the blue line shows the carbon emissions, and the dashed line is the PV offset. On the right, you can see how both energy and the emissions drop after applying the PV system, especially during the peak time. Next, please.
So, all right, so I will talk about how decarbonization shapes space. And I will start from the floor plan in the next page. So you can see the floor plan follows the site design. So as Wasim has said, the shared space is organized around the yard, which can provide everybody have the equal access to the nature, both physically and mentally. And the science lab is located along the north for better controlled lighting, diffuse lighting, and also the thermal environment for executing the precise tasks in the lab. And the classroom is placed along the north and east facade to take use of the daylighting with the good shading. And besides, the site slopes up from south to the north. So the building blocks are at different level. So the parking lots on the north is about 4 feet 6 inches higher than the first level of the northern building block, and is about 9 feet higher than the first level of the southern building block. Next. And this is a rendering showing one of the gathering space. So I will discuss more later. Next, please. So in order to address the operational carbon emission, we need to understand the operational energy usage of this project. So you can see the white shaded bar that shows the cooling load. So for the baseline design, we just use a system called variable refrigerant flow system. So this system just circulate the indoor air through the fans and coils. It doesn't intake any fresh air. And the final EUI is about 59 kBTU per square feet. And we can find the white bar. It shows for this project, the cooling load is dominant, which means if we can reduce the cooling load, so we can contribute significantly to the operational carbon emission. Next, please. Then we look at the thermal balance chart. So the upper one is the same system without any fresh air intake. But we did a comparison study by using the variable air volume system. It involves fresh air intake. And you can look at that white covered bar. So that is the heat loss through the mechanical ventilation. It reduced the cooling load. So we see, oh, the heat loss is beneficial. Then we ask the question, like, can the natural ventilation just has the same impact as the mechanical ventilation to reduce the cooling load if we can place the opening carefully? So the next. But the problem is air pollution is a concern. So many studies shows if children is exposed to the dirty air too early, the dirty air can change their gene some way and cause the adult heart disease. So the Los Angeles air quality is terrible, even though it is getting better and better, but it's still very terrible. So for this middle school, the clean filtered fresh air is critical. Next. So finally, we choose the VAV system with economizer. And the economizer can just cut the EDU by another 15%, reduce the EUI from 59 kBTU per square feet to 38 kBTU square feet. Besides, we also locate the mechanical room on the west-north corner to draw the cleaner and cooler air into the building because it is away from the traffic pollution. And at the same time, it is open to the north side of the building. So it is always under the shade, so the air is cooler. Next, please. So after applying all the strategies, so and excluding summer and winter breaks, the final EUI is about 23 kBTU per square feet. Next, please. And we also look at the outdoor access. So this should be show the total date of the unhealthy air days and also the rainy days. But because this is shared by Sarah, so it is a PDF, so it's not showing the number. Sorry for that. But I'll let you know. So in Los Angeles, the average unhealthy air days is about 100 days per year. And the rainy days is about 20 to 30 days a year. So the total is like 130 days. So which means 1/3 of the year. So like it is not ideal for the outdoor activities. So we ask this question, if all the kids are trapped indoors, so how can we preserve the outdoor benefits on these challenging days? So next. Then we just put one gathering space in each building blocks. So the socials, you can see the social stairs on the right, it actually bridge the elevation changes caused by the slope of the site. And next. Okay, so there are several features like the intimate planting and broad views to the outside, and also the ample daylighting, and also stepped seating and movable furniture. All of these items work together to preserve the outdoor benefits for these indoor spaces. Next. So I would say, like, even though like we have those shared spaces, actually it expands the square footage of the building. People may argue like, oh, it will increase the energy usage and also increase the carbon submission because the volume of the air is bigger and we use more materials to build more square footage. But I would say based on that analysis about the like preserving outdoor benefits and polluted air, so we believe the shared spaces is essential for this project on this site. Yeah. And then we can start talking about how decarbonization shapes experience. Yeah, please, next, please. And we just talk about those challenging days, but during the good days, the things will be different. So the 4D sliding doors will blend the indoor and outdoor spaces. And the outdoor classrooms and the maker space are located on the north of the building. So it is always under the shade of the building. So people will feel cooler. And next. And we also study the exterior, like climate data. It shows there are harmful strong heat stress and also low wind speed. And also the wind direction is mainly from west to the east. Let's go to the next. That's why we installed several like electrical fans to promote the air motion, which can make people feel much cooler. And besides, the form of the building and also the courtyard worked together to form a breezeway from the west to the east to encourage the airflow. Yeah. So next. Then we can talk about something about the sun. So when we talk about sun, it always covers both light and heat. And next. So we coupled both thermal and daylighting simulations together to study like how can we design the sun shading devices? How can we divide the lighting zones and also the electrical settings, including like the base switches, which can provide the adjustable lighting intensity. Next. And I would like to use one example to show how we iterate the design. So this is the eastern windows. Like the big concept is the upper translucent daylighting openings and the lower clear view openings. But if you look at the image on the left, I mean, I asked that question, like, what is the quality of the view? Because it is all blocked by the horizontal deep louver systems. So there are several improvements. So the first thing is the sloped ceiling. It makes us have the higher window, so it can bring the daylighting deeper into the space. And the blend of the framed tilted shading panel and also the horizontal louvers, they work together to provide an interesting look from the exterior and also a broader view to the exterior. Besides, we also integrate the landscape. So the landscape can reduce the depth of panel. At the same time, it also provides a better view for the occupants inside. So people don't have to see the traffic or the residential building around the campus. All right, next. So finally on equity, so the lobby from the parking lot from the north side, so it is higher than the other areas of the building. So we just wonder like if we add additional storefront to add the security. So through the school administration, so that area can be a community cooling center for people to use it. Besides the like the ramp, elevators, and also the platform lift. So they all support the accessibilities and all the bathrooms in this building. So they are all inclusive bathrooms, which improves the transparency, also the flexibility, and it also can reduce the harassment on the campus. All right, that's all about our design. Thank you.
Thank you, Jin and Jian. Really appreciate you sharing your insights. We're going to ask, because we are getting close to time, that the presenters address questions in the Q&A as we go as much as possible. We'll possibly go over a little bit to make sure that we have time to cover the entirety of the last project and maybe answer a few highlighted questions, but that would really help so that at least the questions that have come up get answered as we go. So finally, I'd like to kick it over to Stephanie Perez Ocaranza and Belina Nguyen from Cal Poly Pomona to present their solution.
Everyone's seeing.
Looks like it's loading. There we go. We can see it.
Okay, amazing. Okay, so this is our project, the courtyards. My name is Belina Nguyen.
My name is Stephanie Perez Ocaranza.
So the project is our proposed solution to creating a school that implements zero net energy and low carbon design strategies. We focus on the aspects of photovoltaic design, sun shading, decarbonized resources, and energy storage while keeping in mind how our design will be integrated into the community.
Early climate analysis revealed that the highest need was through passive cooling strategies. Therefore, prevailing winds from the west and some from the east had the greatest impact on the orientation of our building in order to allow for passive ventilation. Next. The form of our building is directly responding to the climate. Studies were conducted to identify the optimal angle of the roof scape for PV generation, leading to a 29-degree tilt for our vertical bar in our project. The effects of the shading structure were also studied in order to bring down outdoor temperatures to a comfortable range, leading to this decision of creating an outdoor trellis structure. Next. Studies were conducted to find the optimal shading strategy for orientation. Shading strategies were chosen based on how much sunlight was needed. Next. Daylight analysis revealed that most rooms are sufficiently daylit. However, the second floor was more lit than the first floor. Next.
So this is our site plan. The site plan shows an aerial view of our design strategies. This includes the 2 integrated courtyards with both private and public access. The private access includes a direct connection to the pre-existing site circulation. And then the roof plan allowed for 3 kinds of voltaic designs that we will talk about in a later slide. This is our ground floor plan that includes our program, including 5 classrooms, 2 labs with a connected workroom, the teacher storage room and work room, the collaboration space, and an art space. The second floor plan is a direct copy of the ground floor plan, which also includes a makerspace that directly connects to the art space below. The second floor plan collaboration space is mostly exterior as it creates a direct connection to our colorful trellis of translucent PV panels. In the larger image, it shows our outdoor collaboration space for students to enjoy contact between the 2 courtyards and showcasing the colorful PV panel trellis. Our intentions for design included understanding the well-being of the students and enjoying each program. The collaboration space and landscaping allowed students to enjoy working together outside and experience a learning outside of their 4-walled classroom. With the term flexible space meaning how students will utilize their spaces beyond these standard size spaces. And then the spaces connect with each other and allow circulation to weave through the programs. All the spaces allow some connection to the exterior space, and our design for discovery strategy included allowing students to directly experience our design towards zero net energy. The colorful trellis shows the indication of how these designs compromise in functionality and aesthetics.
This diagram shows a summary of the sustainable strategies used for this project and its design considerations. Emphasis was given in creating water-safe design, low-carbon materials, flexible design, and an energy-efficient building. Next slide. This diagram shows a summary of the mechanical systems for this project. Defining features in this project were
The implementation of VRF heating and cooling, a mixed mode ventilation to allow natural ventilation under right conditions, the use of LED lights with daylight sensors, renewable energy generation also played a big role in our design. Next slide. For this project, we used 3 main types of PV: monocrystalline, polycrystalline, and amorphous silicone. Monocrystalline panels are found on the sawtooth roofs, which were chosen to blend in with the background. Polycrystalline panels, the most cost-efficient option, are found on flat roofs. Amorphous silicone PV can be transparent and colorful, allowing students to see the possibilities that PV can have on design through a learning by discovering approach, which is used on the trellis. Next.
This is our energy production cycle from showing how the PV systems collect solar energy and convert to usable active energy or on-site storage to the battery storage. The energy could either go to the storage or back to the grid. This decarbonization strategy includes using affordable, locally sourced materials and low embodied carbon materials. Resilient design involves using materials that withstand high impacts and environmental factors. We look to biodegradable natural materials that can be reused in other construction after the building's lifespan. These materials include Accoya wood siding, mass timber structure, bio-based pavers, bio-based linoleum, Cornwall interior cladding, hempcrete for insulation, and aerated concrete block retaining walls.
Design for equity was a driving factor for our landscape design. In order to create an equal experiential path of travel, rather than relying on stairs, the use of ramps was a driving factor for our landscape design. Next slide.
Our garden systems included a variety of native species that could be found from local seed libraries or nurseries. These were selected based on how they could withstand the climate and those that can attract pollinators, and they require little water and good soil. These native plants help teach students to see the benefits of community gardens.
For our overall design process, we started with the mentality with less is more. Therefore, we started to get the lowest EUI, energy use intensity, before PV. So where we started at was at 50 EUI, and with best efforts and implementations of different strategies, each iteration, our UI started getting lower and lower. And next slide, please. With optimization and use of passive ventilation, we were able to achieve a EUI of 18 before PV. And next slide, please. And then with PV, we're able to achieve a EUI of -4 kBTU per feet squared per year. This is the energy breakdown of our building. Thank you.
Thank you.
Excellent work. Thank you so much for sharing your detailed analysis as well as your beautiful renderings and your design solutions. So with that, we actually have a couple of minutes. We can address some of the Q&A questions that have come up. Thank you to all those who have been answering in real time as we go. There is one that hasn't been answered yet. So I believe this one is for the Link Plus project, which is, although structural details and calculations are not part of a competition submittal, what sorts of tests are usually associated with rammed earth, and how is the surface not in need of finishing?
Well, like about the finish, like for removers, like normally we use some gypsum board or some metal, some other thing on top of the structure. But for rim earth, actually we don't need extra gypsum board or some other material on top. We can just leave it with some maintenance and to sand the surface. So it helps save some the finish about the. That's a question, right?
Yeah.
Yeah.
Yeah, I want to add something. And also for the calculation, so actually in the Ladybug, there is no default rimmed earth construction or assembly for calculation. So right now I don't remember the specific resource, but we just we search online to see some researches. They just publish the articles describing like the data and also like the thermal conduction like things data about the rimmed earth they measured. So we use those measures and put it in the Ladybug to build our own rimmed earth assembly for the calculation.
Great. There were also some questions that there were some answers in the chat, but maybe very quickly, if anyone wanted to speak to some of the occupancy schedules, what the assumptions were there, how some of the data showed that there was significant usage in the summer despite the schools often being closed during the summer, and just any afternoon and evening use that might have been anticipated. If anyone wanted to just quickly speak to that.
Sure, I'm happy to do that. So you're talking about the question about between our baseline, like conceptual energy model, and the final one, that in the baseline one, we did show significant energy use over the summer. I remember we were using LAUSD's like calendar for the usage and making some assumptions about like community usage of some of the spaces during the like off times. But I think primarily the difference is between relying much more on mechanical cooling in the initial design than we were once we'd sort of optimized things and figured out those sort of co-benefits between the different systems and stuff. Because I don't think our assumptions about the use of the space changed between the initial and the final design.
Great. Thank you for that. So I think we're at time. Thanks everyone for your attention today. Sarah, any closing comments to close us out here?
Yeah, thank you so much to everyone for